Hi everyone. In this video, we're going to begin talking about energy. Specifically in this video, we're going to talk about two types of energy. The first is work, and the second is kinetic energy. Now, for this introduction, let's actually focus on kinetic energy for a moment. I expect that everyone is familiar with the equation for kinetic energy. First of all, the symbol for kinetic energy, if you really want, you can write it as Ke. The formal symbol for kinetic energy, though, is a capital T, which does obviously share notation with temperature, so just be careful. You've probably seen this equation. Kinetic energy is 1/2 mv squared. Okay, this is the high school physics version of the problem, but let's just consider a case where you have a disk and that disk is rotating about its axis, but it is not translating. According to this equation above it, this disk should have 0 kinetic energy because the center of mass, which is what this equation is tracking, the velocity of center of mass, the center of mass is not moving in this rotating disk, and yet clearly it has energy. So this equation is not actually correct, or it's not complete. There is an additional term, so plus ... There's an additional term in this equation that is going to account for the energy of rotating bodies. So that's ultimately what we want to derive today. We want to get the full equation for the kinetic energy. And another comment about this, in this class we work with vector quantities, and you cannot scale a vector. So this 1/2 mv squared, that is for the magnitude of your velocity vector. We'll talk about how to represent this using vector notation. So where does this equation come from and how do we derive it? The derivation for kinetic energy, it actually comes from the description of work. So we really need to start this topic with work. So what is work? Well, work is when any system acts on another system to elicit some change in motion or trajectory or even temperature. For example, I have my eraser here on this surface, and if I want to move this eraser, I have to apply forces to the eraser. And we know that we have Newton's second law and Euler's second law, where the forces create translational accelerations and the moments create rotational accelerations. Now, the definition for work, so let's say work. The definition of work is actually through integration. You might have seen equations for work in the past that have said work is equal to force times a distance, d. Perhaps you've seen it written as Fx, where x is the distance. This is actually a simplified work equation. The real definition of work is the differential bit of work done is the force. Now this is the sum of forces. I'm just going to drop the sum notation, but consider that we are talking about vectors. So this is a vector of forces. It is the sum of forces dotted with the differential position, so some differential change in position. Now, how do we evaluate this? We could evaluate this simply by integrating, and we could say, let's integrate the work over some bounds, work 1 to work 2, and we could integrate the right-hand side as well from some position to another position. And if this equation, if in this equation the position is changing in one dimension and the force is a constant, and you can bring the force out from here, then the change in work will be equal to a force multiplied by a distance, where it's P2 minus P1. So again, this simplifies down to work is equal to force multiplied by a distance. However, what if your position is following some curved path? What if your force is a function of time or a function of position, etc.? Clearly, this equation becomes more complicated, and we can't perform this, this very quick analytical integration. Here's what we're going to do instead. Let's play with these equations for a bit, and let's try to find a more general way of evaluating this. First of all, the right-hand side, this differential change in position. Let's go to our definition of velocity. We know that velocity is ddt of position. We can actually redefine this then, and I can say that the differential change in position, and we just multiply by the dt, so this is v dt. Let's take that and let's put it into this definition of work. So dw is equal to f dot v dt. What can we do next? Well, let's take the dt and let's move it to the left-hand side. We divide. Now we have ddt of the work is equal to f dot v. And this is much more useful. In this form, we could even write this as w dot if we want. So we're looking at the change in work with respect to time, and this is equal to sum of forces. Again, this is a vector dotted against your velocity vector. Now, how can we solve this equation? Well, again, if you make certain assumptions about the forces being constant with respect to time, etc., you could analytically integrate this. You'll get the same solution that we had a moment ago. But consider, what if you have forces that are changing with time? What if you have a trajectory along some curved path? This answer, or this equation, we can get the answer from numerical integration. Now, if you have not studied numerical integration yet, any undergraduate program in engineering, you will study numerical integration. Consider that you can always take the derivative of an equation, but you can't necessarily integrate every differential equation. In fact, it's very easy to construct a differential equation that you cannot analytically integrate. In those cases, we can numerically integrate these differential equations, and honestly, that's how most equations get solved anyway. You take the differential equation, you put it into a computer, and you solve it using, in the early days, we would use Euler's method. These days, we have much more elegant solvers such as run-cut-of-4 methods. But a numerical integration scheme, you can numerically integrate the w dot as one of your state vectors. If you're interested in seeing this in practice, there are some other videos that I have posted on numerically integrating equations of motion for ballistics, and also in another channel on just the topic of numerical integration in general. Now, one thing interesting to consider about this, work is an energy quantity, and here we're looking at the change in work specifically with respect to time. So the units of w dot would be a joule per second, which is a watt. Just be cautious about symbols and units here. W for work does not mean, W for work does not mean watt. W dot for work does mean watt. So if this is energy changing with time and it has units of watts, W dot is actually a quantity of power. So we have this equation for the power done by a force acting on a moving body. Some applications of this equation, suppose that you were simulating an aircraft, and this aircraft is under the effect of numerous forces. There is the thrust generated by the engines or the turbines. It could be gravity is acting on this rocket. There could also be aerodynamic drag, aerodynamic lift, etc. Many forces could be acting on it. Suppose that we want to calculate the change in energy of the aircraft due to the presence of these forces, or even just one force in particular, or a combination of or a subset of the forces. Suppose that we want to know what's the change in energy specifically with respect to aerodynamic drag. So how much energy have we lost through friction with the air? If you can solve for the aerodynamic drag on your aircraft. This is a vector. You dot that with the instantaneous velocity vector of the aircraft. You solve for W dot, and then you can numerically integrate this W dot value over a period of time in your dynamic simulation. And if your aircraft is going through all kinds of maneuvers, that's fine. You're going to have always accessible an instantaneous velocity vector, and you will always be able to solve for the aerodynamic drag. So inside of your simulation file, you calculate this W dot value, and then you numerically integrate it along with the rest of your variables. And then that will give you a running total of the amount of energy that you have lost due to drag. Now this equation, in the current form, this is only force and velocity. We've talked about rotating bodies, right? I am rotating my eraser right now, and that's not a force, that's a moment. And it doesn't have a linear velocity, it has an angular velocity. So what about rotating bodies? Well, this equation does actually have the rotational analog, where we can say that dW, this time instead of being forces, now we're going to talk about moments. We could do, depending on the application, you might see this written in terms of moments. You might also see it written in terms of a torque. So for example, if you're looking at things like electric motors or pumps or turbines, etc., those are usually described in terms of a torque, which is fine. Okay, so let's do it in terms of moments because that's how we've been talking about it for this course. So it is your moments dotted with, and now it's not a change in position, now it is a change in orientation. So we're going to use the an angle theta to designate the orientation of the body. So we can actually follow the same procedure that we did last time. Let's say that d dt of theta, well, we've described this using angular velocity omega. And quick comment, capital W for work, Greek letter omega for angular velocity, don't get them mixed up. And we can rearrange this. We can say that omega dt equals d theta. Let's take this and replace it in the equation above. So the differential change in work is equal to the moments, which are, again, these are a vector. Hey, little one, where are you going? dW is equal to the moments, which are a vector, dotted with, I'm going to bring this down, omega dt, and of course we divide by the dt on both sides. So ddt of the work, which is, you can also write it as w dot, this is equal to the moments dotted with omega. This form of the equation is useful for things like pumps or electric motors, turbines, etc. And consider it can go in two directions. You could have a situation, let's say a ceiling fan, where you are powering the ceiling fan in order to elicit a change in the motion of the fluid around it. So the ceiling fan is going to have a certain moment or a torque coming onto it, and it's going to be rotating at a certain speed, and then that is the power. In the other direction, think about, this equation can also go the other direction. Suppose that we have an industrial turbine used in energy production. We have some energy source, maybe sunlight from solar panels, maybe fission of heavy elements like uranium. It could be fusion of light elements like tritium and deuterium. We generate some heat, and that heat is used to boil water. The boiling of water produces high pressure, high temperature steam, and that steam is used to spin a turbine. It generates a moment or torque about that turbine, and it spins the turbine at a particular angular velocity. That is the power being generated by the motion of that turbine. That's the change in work done. So we can actually combine the linear, the translation version of work, and the rotation version for a more general expression for mechanics. Let's say that you're working a problem on some kind of spacecraft. So here is your spacecraft, and we want to calculate the work done on your spacecraft through both forces and the moments done. So ddt of the work, we know that in one form this was equal to F dot V, and we know ddt of the work done in the other form was the moments dot angular velocity. Let's combine these, and let's say that the total change in the work is equal to, and I'm going to write this as a lowercase script f dot, oh, it's kind of a weird one to draw. There we go. So this is called var theta. These are spatial notations. So spatial being a 6-dimensional, so I'll say 6 by 1. It's a 6-dimensional description of the problem, and really what we're doing is we're stacking these two equations together. So what this looks like, imagine this spatial force vector as containing both your forces and your moments, and then we're going to dot this with a vector containing both your translational and your angular velocities. So this is a 6 by 1 vector dotted with a 6 by 1 vector, and we're going to get the scalar change in work. Now, some final comments on these equations. Another way to look at this is the power is a combination, it's the product of effort and flow. It's another way you could describe this, effort and flow. And this description actually works for all kinds of power. So we've shown that it's translational power, we've shown rotational power for things like pumps and turbines. This also applies for electrical systems as well. If you have studied any electrical systems, you might have seen the equation for electrical power. Power is equal to I times V. So power is current multiplied by your voltage. And in this instance, your current is your flow and your voltage is your effort. So effort times flow is going to yield power. Okay, so this was a nice discussion of work done. At this point, I expect, or at least I hope, that you could, given some problem, you could take a more complicated description of forces and moments, and you could sort out the work done over some kind of path. If you're able to solve it analytically, you can. If you need to solve it numerically, okay. I tend to represent these when I'm doing numerical problems in terms of dots. So W dot becomes one of my states, and you could take this and you could put it into a numerical integration scheme, and you could integrate and find the work done, or the work done by something. It's always one thing affecting another. So where we need to go next, I'm going to clean this up, and let's go back to the original definition of work, and let's talk about how we can use work to now calculate kinetic energy. I've drawn a rigid body with known center of mass A, and we're going to discretize this rigid body into infinitely many small differential bits of mass. We're going to track those with the point B sub I. We ultimately want to find the kinetic energy of the rigid body A, and the body A can both translate and rotate. Let's begin though by finding the kinetic energy of just that differential bit of mass, B sub I. And let's start with the equation for work. So dW on body B sub I, we know that this is equal to the forces, and again, I could do sum of forces here if I wanted to, but the forces on B sub I dotted with the change in position of B sub I. So first thing, let's do what we did last time in our description of work itself, and let's rewrite this change in position dBi. This is going to be VBI multiplied by dt. So we can take that and we can insert it into the equation above, dWBI, so this is now the forces acting at BI dotted with VBI dt. All right, next. Just going to draw a little divider here and let's talk about the B sub I. We know that the sum of forces on B sub I, this is equal to, we're going to use Newton's second law, ddt of the linear momentum of KBI, and then we know that KBI is MBI VBI. So let's take this and let's insert it into the equation above. So the change in work, this is equal to ddt of MBI VBI dot VBI dt. Next, we can actually cancel the ddt on both sides, and let's say that dWBI is equal to, now this is just the differential MBI VBI dot VBI. Now, what can we do with this? Again, we're going to pause for a moment, and I'm going to suggest, what if we had a differential of the full expression? What if we had MBI VBI dot VBI? And what if we wanted to calculate this? We could do a product rule expansion on this. We're going to treat MBI as a constant. We're not doing any variable mass system here. So MBI is a constant, but the two velocities, these can both change. So we have the derivative of the first term, so I'm going to say d, and I'm going to put the MBI in this one. Now again, the MBI is a constant. We could pull it out if we needed to. I'm going to write it this way just for convenience. Dot VBI plus the first term, MBI VBI dot d VBI. Now again, the MBI can be pulled out. So if I pull the MBI out, and I'm just going to put it over here, consider that these are actually the same thing. So this product rule expansion from above, the full derivative of MBI VBI dot VBI, this is equal to 2 times this, in fact, d MBI VBI dot VBI. So what does this mean? Well, what if I want to solve for this term on the right side? Because that's what I have in this expression above. If I want to solve for it, then we just need to divide by 2. So I end up with a 1/2 over here. The 1/2, this is a constant as well. I could actually move the 1/2 inside. There we go. So what I'm going to do is I'm going to take this, right? This is the term that we have above. I'm going to take this and I'm going to put it into this expression. So dWBI equal to d 1/2 MBI VBI dot VBI. So what we're going to do now is we're actually going to redefine this inside of the parentheses as t. So this is dt of bi. And if we want, we could solve this analytically. I can analytically integrate both sides. And let's say we integrate the left-hand side over some work done. So there is work from one state to a second. And then we integrate this side as well from some energy quantity T1 to T2. So what we get out of this now, first thing we get out of it, well, is just a direct expression for this energy quantity, and T is our kinetic energy. But this analytical integration, what this tells us is that, let's write it W2 minus W1 equals T2 minus T1. Again, the T here is not temperature, it's energy. And we can say deltas. A change in work is equal to a change in kinetic energy. The work done on a system is equal to the change in the kinetic energy of the system. Now, that was just this one description of it. Consider that we didn't put anything into this work calculation that is a potential force. We didn't put any friction or losses, anything like that. So in the event of a frictionless environment where you don't have any other external forces, if you're applying a force to an object, then the energy that you put into it elicits an equal change in the kinetic energy of that object. So really this is kind of, in mechanics, this is called the work energy theorem. Work energy theorem. Really, this is like your first law of thermodynamics, where we say that energy has to be conserved. The energy has to go somewhere. So if you do work on a system, you're going to elicit a change in the kinetic energy of the system. If this is, if we say the friction work, the work done by friction, well, the work done by friction decreases the kinetic energy of a system. So here's my eraser and I give it a little push, and there's friction between the eraser and this surface, and that friction is diminishing the kinetic energy of the system. So there is kinetic energy for a particle, 1/2, and notice that this is akin to what you might have seen, what we talked about earlier, 1/2 mv squared, but notice that it's a dot product. The dot product is the best way to represent it when you're doing vector quantities. If you really want to, you could find the magnitude of your velocity vector, and then you could use that magnitude in this scalar equation, 1/2 mv squared. Just consider, though, that that's actually not particularly efficient, because if we call little v, if this is your magnitude, little v is the magnitude of the norm of your velocity vector, and this is calculated by actually doing the square root of v dot v. So if you want to do this method, then recognize that v squared in this 1/2 mv squared equation, this is really, you're taking the square root of v dot v and then you're squaring it. So that's why I say the best way to represent this is just with a dot product. If you do this in your coding, if you say, the norm of it squared, you're actually wasting resources. And one other final comment, one way that we could represent this, consider that A dot B, this does equal B dot A. Not like with cross products. If you reverse the order of a cross product, you change the sign. With a dot product, though, this is reversible. So, some ways you will see kinetic energy written. I'm going to reverse this. I'm going to put the MBI second. You will sometimes see kinetic energy written as 1/2 V dot K. So again, K being the M times V. So this is another way to do it. This method is also, this representation is useful if you already have the momentum calculated. You can just dot your momentum with your velocity vector. And of course the dimensions here, your momentum is 3 by 1, your velocity is 3 by 1, and energy is a scalar quantity. Okay, so here is our kinetic energy for a particle. What we want to do is we don't want the energy of just the one particle b sub I, we want the energy for the whole rigid body. So let me clean this up and we'll talk about how you sum this up to get everything. We found the kinetic energy of just the particle b sub I, let's find it for the whole thing. The kinetic energy of body A, this is the summation, the infinite summation of the kinetic energy of all of the individual particles, so all of these b sub i's. And we have an expression now for what this was. So let's say the infinite summation of 1/2 mbi vbi dot vbi. And what we want to do, we want to shift the focus away from b sub I. We want to shift the focus to point A instead. So let's redefine the velocity of b sub I using transport theorem. So this is VA plus omega into A cross the position vector from A to b sub I. So TA equals infinite summation of 1/2 mbi. And tell you what, let's put some brackets around this to make it clear what we're doing. And I'm going to bring this definition, I'm going to bring it down here. So omega plus, VA plus omega in A cross P ABI. And we're going to take this term and we're going to dot it with itself. So VA plus omega in A cross P ABI. Now, what's going to happen when we perform this dot product? This expansion is going to get pretty big. We're going to get, we're going to do a foiling operation. So we're going to get VA dotted with VA. We're going to get VA dotted with this one. We're going to get the first one dotted with VA, and then we're going to get that term dotted with this one. So what I'm going to do, let's clean all this up. And clearly we're going to get 4 terms out of this, and I have them written here, so I'm actually just going to read these off of my notes because they get kind of nasty. So TA is equal to, so we're going to get 4 terms out of this, and I'm going to do a little simplification along the way. So here's the first term, VA dot. Let's write this as, here's the infinite summation of MBI and VA. So that's just the first term. This was the VA dot VA term. In this one, notice that everything is constant with respect to the integration with the exception of the MBI. And if you sum all of those individual MBIs, you get MA, the mass of the whole thing. So this expression now, this is going to be 1/2 MA VA dot VA. This was that kinetic energy of the particle. But notice now we're looking at the velocity of the center of mass and the total mass of the whole thing. So there's the first expression. The second, here we go. So 1/2 VA dot omega in A. These were both constant with respect to the summation, and here's the remaining term. Summation of MBI P ABI. And recall from previous derivations that this quantity, we know that this is equal to 0. That comes from definition of center of mass. Now, the third term in the expression is the same thing as this, just rearranged. VA dot, here's our infinite summation term, MBI, PABI, and of course this term is going to equal 0 as well. And the rest of this expression, it was 1/2, here we go. This is the omega in A cross this term, dot VA. There we go. Okay, there was expression 3. Same thing though. This is these two are just the same thing rearranged, right? Resulting from that the expansion of the previous term, and these are both equal to 0. And then here's the last term, and this one might look kind of nasty at first, but we're going to deal with it. So the infinite summation is now out front, and I'm going to write it as omega NA cross P ABI dot MBI omega NA cross P ABI. Now, there are quantities changing with respect to the summation throughout this description. The best we could do if we wanted to is pull this omega NA out front. Now, what's going on here? This has a name as well. We've seen vector triple products in the past. This is called a scalar triple product. And we have some useful identities for this one as well. So what I'm going to do, I'm going to erase these ones in the middle because we're done with them. So our kinetic energy of a rigid body is going to be, and we can actually rewrite this one on top as well. Let's say it is TA is equal to 1/2 VA dot MAVA. So again, we could write this as velocity dot linear momentum plus this thing on bottom. So here is your identity for a scalar triple product. If you have A dot B cross C, this is equal to B dot C cross A. And here's how we're going to arrange this. Let's make this part our C, and the next part A. Oh, here we go. Sorry. This last part is C. There we go. And the part in front, this is A, and this is B. There we go. So if we arrange it in this way, then when we use our triple product identity, here's what we get. So I'm going to move this one up here. TA is 1/2 VA dot MAVA. And the second term is plus 1/2. I'm going to do the C cross A part first. So let's take our C, which is P ABI, and we're going to do C cross A. We need to have our infinite summation out here. Okay. So C cross, the A term is omega NA cross PABI. And then let's bring up the B. So the B was MBI omega NA dot. There we are. And this infinite summation, of course, it applies to the whole thing. Now, we can clean this one up just a little bit. Let's bring this omega NA out to the front. So I'm just, there we go. So we have 1/2 VA dot MAVA. Okay. And what I'm going to do is I'm going to rewrite this one. So plus 1/2, I'm going to bring the omega NA out front. So it's omega NA dot. Here's our infinite summation. I'm going to leave the mass on the inside. Of course, the mass is scalar. We can move it anywhere in this expression we need. And now we have PABI cross omega into A cross PABI. Now this part becomes a vector triple product. But we've actually seen this exact expression before. We saw this when we derived angular momentum. This quantity is IAA times omega NA. So what happens to this whole expression when we put everything together? At the end of all this, our kinetic energy is 1/2 VA dot MAVA plus 1/2 omega dot IAA omega NA. And we can rewrite this if we want to. We could say the kinetic energy of a rigid body is 1/2 its velocity dotted with its linear momentum plus 1/2 its angular velocity dotted with its angular momentum. And notice that in this case, it is specifically velocity of center of mass and angular momentum about its own center of mass. So the inertia is IAA. It doesn't matter what else the problem is asking for. We know that we could find angular momentum of this body about any point at all. But when we go to calculate kinetic energy, it is always the inertia about its own center of mass. So if you're doing, if you're not changing mass, if you're not burning fuel, anything like that, then your mass and your inertia, these are constants, and you simply find expressions for the velocity of a body. You can dot those two velocities together to get a scalar. You find the angular velocity, you dot that with inertia, and then that's multiplied by angular velocity again. And you get, from both of these, you get a scalar energy quantity. Now, what if we have a series of rigid bodies? We've done mechanisms like 4-bar linkages. We've done mechanisms like crank sliders, for example. And suppose that we want to know the total kinetic energy of this system. Well, let's call these bodies A, B, and C. The kinetic energy of the system is the sum of the kinetic energies of each of the individual bodies. And you can just find each of them individually and then add them all up. All right. So there's videos for worked examples where we calculate kinetic energy for problems. I'm also going to make a video. This video we did work in kinetic energy. I'm also going to make a video where we derive potential energy expressions, and we'll look at gravitational potential, and we'll look at potential in springs as well. And once you see that process, you could then turn around and you can calculate potential in a magnetic field, potential in an electric field, etc. All right, so that's it for this one. Best of luck, everyone. I'll see you around.